Hi all. All right. So, if we're trying to get a handle on what is the temperature of this exoplanet we've discovered, what's it like on there? The effective temperature is essentially a good first guess. It's a good first estimation for what the temperature of the planet should be. Why? Why do we say that that's our good first guess? Well, the effective temperature is the temperature of the planet at which the energy absorbed from its parent star and the energy that it re-radiates out into space are in equilibrium. Which is a complicated way of saying what? It's a complicated way of saying a planet is receiving energy from the light of its star, right? The starlight shines on the planet and the planet warms up. And the surface of a planet it's a black body. It's a warm, dense object, and any warm, dense object is going to give off its continuous spectrum. So a planet is being warmed up by the star, but it cools itself off by re-radiating that heat back out into space. And when the energy coming from the star and the energy that it loses out to space are in balance, that's the effective temperature, or I should say, the effective temperature is the temperature that the planet warms up to, such that those two things are in equilibrium. I've got an explanation. I've got a little more explanation here in a second, but to cut to the end first off, the effective temperature it's the prediction. It's what you predict the temperature of the planet should be when the energy in and the energy out are equal. And the effective temperature depends on what? It depends on the luminosity of the star. If the star is brighter, it's going to heat up the planet more. It depends on the distance between the planet and the star. If the planet is farther away from the star, then the planet should be cooler. And it also depends on the albedo of the planet. What is that? That's something we haven't talked about before. Albedo is a term for essentially how reflective the planet is. How much of the incoming starlight gets reflected off the planet and back out into space. If a planet has a high albedo, then it reflects a lot of light. And any light that gets reflected is not going to be absorbed by the planet, and therefore it cools off the planet. Right? A planet is only warmed up by the energy that it absorbs, the energy in. And so if the light comes in, hits the planet, and then just reflects off into space, then it's not absorbing that energy, and that energy that gets reflected can't warm the planet up. A planet with a low albedo reflects less light, and so it absorbs more light. And if it absorbs more light, then it's going to warm up the planet more. So, let's put all these things together. All right? Let's start from, all right, you've got the surface of the Earth. Some sunlight comes in, and some of that sunlight is going to reflect off back out into space, but here we're just going to count the energy that does get absorbed. So let's imagine at the very beginning, the Earth is cold. If the Earth is cold, then some sunlight comes in, that sunlight gets absorbed by the surface of the Earth, and the planet warms up a little bit. And if the planet warms up a little bit, then it's going to give off its continuous spectrum. It's going to give off, that the surface of the Earth is a hot, dense body, and so it's going to give off some luminosity. It's going to give off some energy back out to space. But the Earth is still just warming up. It's not very hot yet, so it can't give off very much energy. So if the energy coming from the sun is more than the energy that the Earth is losing back out to space, then the planet warms up some more. And if the planet warms up some more, it can give off a little more energy. but they're still not in balance. The energy coming from the sun is still more than the energy the planet is losing. So then the planet warms up even more, and when the planet warms up even more, eventually the planet becomes so bright. Eventually the planet's continuous spectrum is radiating energy back out into space, which is to say, the planet's luminosity is losing energy out to space at the same rate that the planet is gaining energy from the sun. Sunlight comes from the sun, it gets absorbed by the Earth warms up, but then it loses that energy back out into space, and the planet goes back to the temperature it was at before. They're in balance. The energy in is balanced out by the energy out, and then the planet stops heating up. The planet's not gaining any more net energy. The planet is just, the temperature of the planet is just held at a steady temperature. And that's what the effective temperature is. The effective temperature is the temperature that the surface of the planet has to be warmed up to until the energy out equals the energy in. And then the temperature stabilizes. Okay, hopefully that makes a little bit more sense. It's a little tricky, I'll give it to you. This is a little bit of a tricky topic. So how do we figure out what that effective temperature is? Okay. Well, the effective temperature is going to depend on the flux of starlight, right? Because when we talk about the energy absorbed from the sun, that's another word for the flux. And the flux of starlight shining on a planet depends on the luminosity of the star, but the exact same equation that we were using at the beginning of the semester, take that luminosity, divide it by 4 pi times the distance squared. You're taking this luminosity from the star, you're dividing it over this area, over the surface area over which that light is distributed, and that gives you the amount of energy per unit area, the amount of energy per square meter, and that's what flux is. So, like we talked about at the beginning of the semester, this equation works, or this equation really only works, if you have the luminosity in watts, you have the distance between the star and the planet in meters, and then when you plug them in there, you'll get the flux in watts per square meter. So now we have the intensity of sunlight, the intensity of starlight shining on that planet, right? Flux is a measure of intensity. How bright, how intense is the light from that star shining on its planet? And then the temperature that the planet warms up to is this relationship, right? The effective temperature depends on, right? The effective temperature is how much the flux warms up the planet to, how warm the planet is heated by that flux. So the effective temperature depends on the flux, but then you're multiplying by 1 minus albedo. Why? Well, remember, albedo is the fraction of light that gets reflected off the planet. So if the albedo is the fraction of light that gets reflected away, then 1 minus the albedo is the fraction of the light that actually gets absorbed by the planet, and it actually warms up the planet. So when you take the flux times 1 minus the albedo, this whole numerator here, the flux times 1 minus the albedo, that's the actual amount of energy from the star that's warming up the planet, right? So you take this, and then you divide by 4 sigma, right? Sigma is the same Stefan Boltzmann constant that we used a little earlier in the semester, right? So it's just a constant. The sigma is just 5.67 times 10 to the negative 8. So this isn't a variable. This is always just going to be the same 4 sigma. Take all of that to the 1/4 power, and you've now figured out, okay, what temperature must the planet be warmed up to such that it is losing energy at the same rate that it's being absorbed by the absorbed flux from the star. Okay. So how are we going to do this math? Well, let's have our calculator do this for us. Let's program our spreadsheet to do this for us. So I've got my spreadsheet already kind of formatted nicely. First things first, let's figure out the flux of starlight shining on the planet. So I've set this up to be like the Earth, right? The Earth is orbiting a 1 solar luminosity star. The Earth is orbiting the Sun at 1 AU, and the Earth's albedo is about 0.3. So I've just put in some numbers to calculate the effective temperature of Earth. All right. First thing to do is calculate the flux. Oops. Back. There we go. And so we need to convert the luminosity into watts and the orbital distance in... Sorry, the computer's acting up. Calculate the orbital distance in meters. All right. So, how are we going to convert from solar luminosities into watts? Well, 1 solar luminosity is 3.839 times 10 to the 26 watts. So if we have our spreadsheet, take the number of solar luminosities, multiply by the number of watts per solar luminosity, 3.839 times 10 to the 26. Okay, then that'll calculate the luminosity of the star, in this case the Sun, in watts. Now let's convert the orbital distance into meters. So we're going to do that by taking the number of AU and then multiplying by the number of meters in 1 AU, which is 1.496 E11. All right. So that'll convert the orbital distance or the orbital radius or the semi-major axis. 3 ways of saying the same thing. So let's take the radius and let's calculate what 4 pi times the orbital radius or orbital distance, again, same thing. Let's figure out what this denominator is, and then we'll just do luminosity divided by 4 pi distance squared. So, 4 pi, I just wrote 4 pi r squared just as a note to myself to say, oh, this is what I'm calculating here. Okay, equals 4 times pi times the orbital radius squared. Okay, so that'll determine the surface area of the bubble over which the luminosity is being spread as it travels away from the star, and therefore the flux is just luminosity divided by 4 pi r squared. So the flux equals luminosity divided by this thing we just calculated. All right, so the flux of sunlight shining on the Earth, since we put the luminosity in for the Sun and the orbital distance for the Earth, the flux of sunlight shining on the Earth is 1,365 watts per square meter. All right, well, what effective temperature does that equate to? So the effective temperature, and I'm going to make a little bit of room because this is going to be a longer equation. So let me make some more room for myself here. All right. How do we take a big complicated formula like this and make sure we program our spreadsheet correctly? Let's do it in small chunks. Okay? So we're going to take this and say equals, let's do 1 minus the albedo. So 1 minus the albedo. And again, albedo, notice I didn't put a unit here because an albedo is a unitless number, right? Albedo is just a fraction. It's what fraction of the light is reflected off the planet. So I've got 1 minus the albedo. Okay. And then I take that, I multiply by the flux. So I'm going to say, all right, the flux is that right there. So now I've got flux times 1 minus albedo. Okay. That's my numerator. So I'm going to wrap that in parentheses, take that whole thing, and then divide by my denominator, and I'm going to start parentheses there to say, all right, what's the denominator? It's 4 times sigma. So 4 times sigma. What is sigma? It's 5.67 e minus 8. So 5.67 e negative 8. Close parenthesis. All right, so I've got my numerator divided by my denominator. Now I just need to wrap that whole thing in parentheses and take it to the 0.25 power. So wrap this whole thing in parentheses and raise it to the 0.25 power. And okay, that'll give us the effective temperature in Kelvin. So when the Earth is warmed up by the sun, 1,300 watts per square meter hits the Earth. 30% of that just bounces off the Earth and back out into space. The other 70% actually gets absorbed by the Earth, and the Earth warms up to 254 Kelvin. Okay. All right. And that is the correct effective temperature. So, definitely going to save this to my spreadsheet, so that'll save me a lot of energy when I'm doing these kinds of problems later. So, if we look at Venus, Earth, and Mars, what kind of effective temperatures do we expect from these planets? Well, we got this right. Okay, so I must have done my math in the spreadsheet correctly. All right. Venus is closer to the sun. And since Venus is closer to the sun, the sunlight is more intense. The flux of sunlight shining on Venus is greater. But here's the weird thing. Venus is covered in clouds. Venus has a thick atmosphere of clouds that cover the whole planet. So the cloud tops there are very reflective. Venus has a really high albedo. So the sunlight is really intense shining on Venus, but most of that light just bounces off the clouds back out into space, and it doesn't actually heat the planet up. And so since a lot less of that sunlight gets absorbed to warm the planet, then the effective temperature predicts that Venus should be cooler. It should only be 184 Kelvin. Mars is farther from the sun than Earth is, and therefore it's got less flux of sunlight shining on the planet. The albedo of Mars is about the same albedo as Earth, so that doesn't change much. But because the sunlight is less intense on Mars, then the effective temperature says it should only be warmed up to 210 Kelvin. Okay, here we go. So, as I said, the effective temperature is a good first guess about what the temperature of this planet should be based on the flux of starlight shining on it and the albedo, how reflective the planet is. But it's just an estimate. The effective temperature is your first estimate of the temperature. Well, we know what the actual temperatures of these planets are, right? Earth, Venus, Mars, we don't have to estimate. We can get the actual temperature. And the actual temperature of Venus is, 735 Kelvin. Those don't match. The actual temperature on Earth is 288 Kelvin. Also doesn't match. The effective temperature on Mars, almost matches. 220 Kelvin. What's going on here? Why doesn't the effective temperature match the actual temperature? Well, because the effective temperature is too simple of a model, right? The effective temperature just assumes, right? This whole effective temperature model assumes that a planet is just a rocky surface with some sunlight shining on it. It loses that heat back out to space, and the planet stays at that temperature. There's more to a planet than just a rocky surface that can absorb some heat. What else do Venus, Earth, and Mars have besides a rocky surface? They've got an atmosphere. And so that's going to add a wrinkle to our calculations here. Mars has an atmosphere, and that atmosphere warms up Mars by a little bit. Mars doesn't have much atmosphere. Right? If a planet has an atmosphere, that atmosphere can help warm up the planet by, well, a little or a lot, depending on how much atmosphere we're talking about. Mars has a really thin atmosphere, and so Mars's atmosphere only warms it up by, about 10 degrees. Earth has a little more atmosphere, and so Earth's atmosphere warms up the planet by about 30 degrees. Venus has a really thick atmosphere. It's so thick you can never see through it. There's never a clear day on Venus. Venus is always covered in this thick blanket of clouds. And that really thick, dense atmosphere warms up Venus by a lot. So like I said, the effective temperature is a good first guess. It's a good prediction for what the temperature of a planet should be. But if you want to get the whole picture, then we got to figure out how much extra warming we're going to get on the planet's surface caused by the atmosphere. How do we do that? That'll be the topic for the next lecture. So, the effective temperature is not perfect, right? As I said, it's a good first guess, but it's a simple guess. If a planet doesn't have an atmosphere, if a planet really is just a rock with some sunlight shining on it, then, go back there. If a planet really is just a rock with some sunlight shining on it, then the effective temperature model works pretty well. But if you add some atmosphere around that planet, then you got to take that into consideration too, in order to get a handle on what the temperature really is. And you want to know what the temperature really is in order to figure out things like, what's the water like? What phase is the water in? So all of these things are tied together. Okay, so let's get some practice calculating the effective temperature, and then we'll move on to the next topic, which is, what effect is the atmosphere having on these planets? Okay. Have a good one, everybody, and I'll see you in the next topic.